Here are some problems from chapter 18. If you'd like to work through some of these before I explain them, you can pause the video and then we'll cover how to do them. So for the first set of problems up here, we're going to be doing reactions of acyl halides. That's your carboxylic acid structure, but it has a Cl instead of an OH. So let's work from the upper right down and around clockwise. Now if we're going to add RNH2, where R is any carbon chain, what's going to happen is we're going to add on this N where the Cl was bonded. The N will have this R group bonded to it and one of these H's. So you essentially lose an H on the N when you react some sort of R or N group with an acyl halide. So there's our N, and it's going to have an H and an R prime. Okay, now if we go down to the NH3, we'll get an R bonded to our C double bond O. Now instead of NH3, it's going to be NH2. Because remember, we lose one of our H's. Alright, and then when we add in this structure right here, which looks like a carboxylic acid without the H, we're going to end up forming a structure called an anhydride, and that looks like this. If we add water to our acyl halide, we're going to go back to our carboxylic acid. And then finally, if we add in this HOCH3, we will go to an ester. Okay, moving down to base hydrolysis of amides. So when we add in NaOH to our amide, the structure that we get looks like this. Sort of a weird end product, right? Because we have an O- left over. But let's look at the mechanism to see how we get this. So in the first step, we will take an OH from our NaOH. Pair of electrons attack this carbonyl. So that's what we get after the first step. Now in the next step, the next part of this mechanism is elimination of the NH2 group. Now NH2 is a very poor leaving group, but it is also a very strong base. So when we kick it off, it's going to find a molecule of water and steal an H away from that water to make itself NH3. So first we're going to have electrons on this O-. one pair of these electrons will come down and make a double bond between O and C. That kicks off NH2, but the electrons that we just kicked off onto NH2 find a molecule of water, and that makes this NH3 now. And then we also just created another OH minus. So in the following step here, what we're going to do is deprotonate this H right here on the OH with this OH. Now, this is a driving force because since the equilibrium lies so much towards the anion, which is the O minus form here, by deprotonating this H, we make it go towards the equilibrium. So these electrons on the OH will steal this H, which pushes electrons, which there's a bond between here, onto the O. So we end up getting this for our product. Now in this last example that we have, this is a reaction of an ester with a Grignard reagent. And what happens here is we actually get 2 additions of Grignard, and that's due to the fact that we have an ester to start. So the final product looks like this. So now we have 2 benzene rings bonded to the central carbon. Now the steps that are involved here, so in the first step, if we have our Grignard, remember the electrons between the Mg and the carbon group will attack the carbonyl. Now, we push electrons up onto this O, but with an ester or any OR group, as soon as those electrons go up onto the O on the carbonyl, they come right back down, reforming this double bond, which kicks off the OR group. So there's 1 Grignard. Now remember, as long as you have a carbonyl left, Grignard continues to react, as long as it doesn't say only 1 equivalent. So we take another Grignard, we again attack the carbonyl. Now this time when the electrons get pushed up onto the O, there is no OR group to push off. There's only carbon groups, and we can't do that. so the electrons stay up there. And that's how we get this final product. And then of course you can add in a dilute acid to protonate that O- and make it an OH group.